In this video, we derive the formula for the distance between a point and a plane, and we'll also look at taking that distance formula and applying it to two parallel planes. So if you're trying to determine the distance between two parallel planes, you can use this formula as well. So this is the plane and the point for our example. But before we do that, let's imagine we've got a plane. It's got lots of points in it. I'm going to call one of those points P. It has coordinates, let's say x naught, y naught, z naught. And let's say we're interested in the distance between this point and this point Q, which is not on the plane. Actually, I don't even think I needed to label that in order to come up with our formula. That's okay. So I've got P here in the plane. This plane has a certain normal vector, n. And we want the distance between this plane and Q. Now I'm going to make my plane a little bit larger. Looks a bit like a rug. Whenever we say the distance between a point and a plane, what we really mean is the shortest distance between a point and a plane. Like one distance between Q and this plane is the distance from Q to P. But we all know that the shortest distance between 2 points is a straight line. The shortest distance between P and Q is obviously the straight line between them. But if I want the shortest distance between Q and this plane, basically I want this distance that goes straight down from Q directly onto the plane. All those other distances from Q to the plane are going to be longer, so we're looking for the shortest distance between Q and the plane. Now you might notice, well, that distance, well, that's perpendicular to the plane, so that means that this is parallel to this. But it's not necessarily the same length. N could be as long as we want it to. N could be pointing in the opposite direction. We can always shrink N. So the question becomes, how do I get that distance, the distance between Q and the plane, knowing that that distance that I'm looking at is parallel to N? Well, we can take, we can do a little bit of geometry. Now, rather than using this point as P, I think I want to, or actually I think I will use that point as P. I'm just going to draw my normal vector over here instead. So here's another version of the normal. It's still at a 90-degree angle pointing up. Now, in order to find this distance, I'm going to create a vector that starts at P, a point in the plane, and goes to Q, the point outside of the plane. Do you guys see that this is N and that's PQ, so the angle between P and Q is right there, or the angle between N and PQ is right there? What we want is this distance. It's a little bit hard to see. We want that distance right there. Do you remember what that is? Well, it's the part of PQ that is lying in the direction of N. But I just want the distance. I don't even need the vector. So what I'm saying is, the shortest distance is the projection of PQ onto N. Another way to look at it is if this is theta, that shortest distance, this side is adjacent to theta. It's going to be the hypotenuse, the length of the hypotenuse, which is the length of PQ, times cosine of theta. We're going to force it to be positive because it's distance. And then we're going to say, okay, that looks an awful lot like a dot product. If I knew that angle theta, I would just go ahead and evaluate it. I would just evaluate it like this. If I knew theta was 45 degrees, I'd just plug in 45, find the length of PQ, and multiply. But the truth is, most of the time we don't know that angle theta. But we do know n, and we can find PQ in component form. So we're going to use the same trick that we used earlier when we found the projection. We're going to multiply by the length of n and divide by the length of n. And so we get PQ dotted with n over the length of n. Or if you prefer, you can just think of it as the length of the projection of PQ onto n. This is probably the formula I'm going to use. Geometrically, this is what we did. We found the part of PQ that was lying in the n direction. Or, just using trig, we can derive it the same way we derived our projection formula. We get the length of PQ times cosine, and if we multiply by the length of n over the length of n, we get this formula over here. So this is the shortest distance between Q, a point not on the plane, and a plane that passes through the point P and has a normal vector n. So that's our derivation. Let me write it out in words for you. The shortest distance between a plane containing the point P, and P can be any point in the plane. If we were really fortunate, we could have found this point P. P could be right here, and we just find the distance between P and Q, and that'd be enough. But, I mean, we really don't know. When we're finding points in the plane, we don't know if it's right there, or if it's there, or if it's there, or if it's there. We have no idea. So P is just any old point in the plane. And we're taking the shortest distance between the plane containing P with normal vector n plane containing P with normal vector n. So it's the shortest distance between this plane and a point Q. I want to say that the point Q is not on the plane, but even if it were in the plane, if Q was down here, PQ dotted with n would give me 0. And we'd immediately see that the distance between Q and the plane is 0. So this even works when Q is in the plane. And I'm going to write distance equals, and this is what I'd put on my note card. I'm creating a formula sheet. Or if you prefer, you can put the projection of PQ onto n, which is equal to this. Same thing. All right. So now let's apply it. Let's apply this distance formula to this plane. So I've got a plane, and it has a normal vector. And the normal vector, again, can be found by reading off the coefficients of x, y, and z. So its normal vector is 3, -4, 5. And the point Q has coordinates 1, 3, -1. In order to use this formula, I have to find a point P in this plane. Any point in the plane would work. So remember, you've got 2 free variables here. Choose 2 of them, and then the third is implied by the equation. Since I know that 3 and 6 have a factor in common, I think I'm going to let y and z equal 0. So choose 2 values of 2 of these variables, And then once you know that y and z are both 0, then you have 3x has to be 6, so x must be 6 divided by 3, which is 2. So x, y, z, one point in the plane is just 2, 0, 0. All right, so that's P. And I can draw my normal over here if I want to. Same normal as before. We're going to find the vector PQ. We're going to take the projection of the vector PQ onto n and find that distance right there. Okay. Okay, so I guess we need the vector PQ. Start at Q, and then you want to subtract the coordinates of P. So do subtract 2, subtract 0, and subtract 0. So we get -1, 3, -1. All right, now that I have done that, I want to dot it with n. So I've got -1, 3, -1, and I'm dotting that with 3, -4, 5. So we have -1 times 3 plus 3 times -4 plus -1 times 5. So we get -3 minus 12 minus 5. So that's -8 minus 12 is -20. And we need the length of n in the denominator. So n had these components. That's our n. So remember, we take them, we square them, we add them, and we take the square root. So that's 9 plus 16. That's 25, plus another 25 is 50. So we've got square root of 50, or if you prefer, you could write that as square root of 25, which is 5, times the square root of 2. Okay, so now we're ready to write down our distance. It's the absolute value of PQ dotted with n, which was -20, and then we're dividing by 5 root 2. 5 goes into 24 times, so we get 4 over root 2. Or you could rationalize if you prefer, and we get 4 root 2 over 2, which is 2 root 2. Okay, so let's recap. How did we do this? Someone says, find the distance between this point and this plane. You have to first find the normal vector to the plane. And you find the normal by reading off the coefficients. Second, you have to find a point P in the plane. Now we had this plane, it was given to us. In order to find a point that satisfies this equation, you can choose 2 of the variables and infer what the third would have to be. I chose y and z equals 0, and then x would have to be 2. So 2, 0, 0 is in the plane. I could have just as easily chosen x and y to be 0, and then I'd have 5z equals 6. So we'd have 0, 0, and 6 divided by 5 as our coordinates. You can pick any 2 you want, and they don't actually have to be 0. You could put in 1 for x and 1 for y, and then solve that for z and see what z would have to be. So you'd have 1, 1, and that z value as a point in the plane. So you find the normal, then you find the point in the plane. Okay, then you need to find the vector PQ. You do terminal minus initial. the coordinates of Q minus the coordinates of P, simplify. Then compute the dot product of PQ with N. Then you want to compute the length of N. And then you substitute into the formula. That's the absolute value of the dot product right there. And in the denominator, we've got the length of N. So we substitute, we simplify, and we're here. Alright, so that's how we find the distance between a point and a plane. We're going to do one more. It says find the distance between the two parallel planes. Actually, this is pretty much the same thing. Now, first we need to confirm that they're parallel. I've got some plane down here and another plane up here. I'm not really sure which one is which, so I'm just going to call this plane 1 and this one plane 2. How do we know that they're parallel to each other? I hope you can see it. I hope you can see the coefficients of this plane and this plane, they're exactly the same. So what does that mean, guys? We have the same normal vector. This one has a normal vector with components 4, -4, and 9. And so does this one. Now, many students are tempted to say the distance between these two planes is 11. Just do 18 minus 7. But that's not necessarily the case. In order to find the distance between the two planes, we need a point in one of the planes, and then we'll find the distance between that point in one plane and the other plane. So I think, let's say that our point Q is in the second plane, and I chose the second plane because the arithmetic will be easier, because I know that 9 goes into 18 twice. So let's find a point in plane 2. So I guess the first step is to confirm that the planes are parallel. By showing that the normals are the same. N1 and N2 are equal. And they are. Now, this one could be a constant multiple of this one, and they would still be parallel. If this was multiplied by 2, that normal vector would just be twice as long. Or if it's multiplied by -2, it would be twice as long and in the opposite direction. So, first thing we do is confirm that the planes are parallel by showing that this one is a constant times this one, and it turns out the constant's 1 this time. Next, we are going to choose a point P, or point Q, in plane 2. And to choose that point Q, I can choose two values for x, y, or z. Choose any two values for two of these variables, and then the third will be implied by the equation. So I'm going to choose x and y to be 0. Then in the equation for plane 2, we're going to have 4 times 0 minus 4 times 0, so that's 0, plus 9z equals 18. So z must be 2. So we've got a point in the plane, it's 0, 0, 2. So that's Q. Now, in order to do this, remember our distance formula. We need a point not in the plane. We need a point P in this plane. we need the vector from P onto Q, or from P to Q, excuse me. And then we need to take the dot product of PQ with one of these n's and then divide by the length of n. Now the geometry is not as obvious because of the way the vectors are pointing, but I could just as easily flip this one upside down and make it point this way. We want the projection of PQ onto the normal vector n. That's going to be that distance between the two planes. Okay, so I need a point P in the first plane. So I want to choose or find a point P in the first plane, plane 1. Now you do not have to draw this picture in order to do this math, but the picture really helps me to keep track of what I'm doing. You might accidentally use the same plane twice when you're finding P and Q, and then you're going to be in trouble. It's not going to work out. You need a point that's in one plane. That's your point not in the plane, and then a P, and then the point that's in the other plane. So we're finding right now the distance between this and Q is the same as the distance between plane 1 and plane 2. So let's find P in plane 1. You can use any x's, y's, and z's that you want. Even though I'm not really in love with the idea of having a bunch of fourths fractions here, I think I'm just gonna go with it. That's okay. I'm just gonna let y and z equal 0. Then we'll have 4x equals 7. Because if this is 0 and this is 0, all we're left with is a 4x and then a 7 on the right hand side. So we'll divide by 4. And that's, well, 7/4, so 175. Okay, so 1 point xyz is 7/4, 0 and 0, or you can use 1.75 if you prefer. Okay, now I need to find the distance, and in order to use this formula, I need to find the vector from P to Q. I need to dot it with n, and then I need to find the length of n. Okay, so let's compute the vector from P to Q. So we start with the coordinates of Q, which were 0, 0, 2, and we subtract the coordinates of P. And so we get -7/4, 0 and 2. Okay. And that's our PQ. All right. Looking at our formula, what do we need next? We need the dot product of PQ and n. So I'm taking that and I'm dotting it with n, which we saw earlier was 4, -4, 9. So we've got -7/4 times 4 plus 0 times -4 plus 2 times 9. So those 4's reduce. You get -7 plus 0 plus 18. So that's 11. And then we need to compute the length of n, the length of that normal vector. Remember how we do that? Take the components, square them, add them, and take the square root. So we've got 16 plus 16 plus 81. So that's 32 plus 81. 113. All right, so what's the distance? You're going to substitute all those values into your formula. and simplify. A lot of students, they look at this and they say, the distance between the planes is obviously 11, I just subtract them. If you subtract them, you're going to get 0 equals 11. That's not true. So it's not the distance between the planes. Distance is PQ dotted with n in absolute value divided by the length of n. So we get 11 over the square root of 113. We can stop there. If you don't want to stop there, you don't have to. You can rationalize if you prefer. Oops, that should be without the radical now, 113. Okay, so we either get this or we get this. And that's it. That's how we find the distance between two parallel planes. It's pretty much the same as finding the distance between a plane and a point. You just have to make sure that one point is, or the point Q is in one plane and the point P is in the other plane. Then you find the vector from P to Q and you just use the formulas.